Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into an interesting piece titled From Tokens to Thoughts, How LLMs and Humans Trade Compression for Meaning. It's a fascinating look at how large language models, or LLMs, process information and how that relates to human cognition. What are your initial thoughts on this?
Well, I think it's a really relevant topic, especially given the explosion of LLMs like GPT-4 and others. The idea that these models are essentially compressing vast amounts of data into tokens and then using those tokens to generate text is pretty mind-blowing. It definitely speaks to the power of deep learning.
I agree it's relevant, but I'm not entirely sold on the idea that compression equals meaning. It feels like we're equating pattern recognition with actual understanding. These models are amazing at predicting the next word, but do they really understand the underlying concepts?
That's exactly where my head went. It feels like brute force. Throw enough data at a problem and you'll eventually find patterns. But does that mean the system actually understands the problem? I think we're missing something fundamental about how true intelligence, human or otherwise, works. It's got to be more than just compression. Maybe it's how they navigate through different representational spaces, how they connect abstract concepts to the real world in a spatiotemporal sense.
That's a great point. The article hints at this trade-off between compression and meaning, almost suggesting they're inversely related. The more you compress, the more you lose some of the nuance, the meaning. But the question is, how do we define meaning in this context? Is it simply the ability to generate coherent text, or is it something deeper?
I think the ability to generate coherent and contextually relevant text is a form of meaning, at least in a functional sense. Look at how LLMs can answer complex questions, translate languages, even write code. That all requires a level of understanding, even if it's not the same as human understanding.
But that understanding is based on statistical probabilities, right? It's not like the model has a mental model of the world. If you ask it a question that falls outside of its training data or requires a bit of common sense reasoning, it often falls apart. It can't generalize well.
Exactly. It's like it can tell you the definition of a car and even write a poem about a car, but it doesn't actually know what it's like to drive a car or understand the purpose of a car in society. It's missing that embodied, contextual understanding. And I think that spatiotemporal reasoning I mentioned is key to that understanding. Knowing where a car is, how it moves, its relationship to other objects in the environment.
So let's dig a little deeper into this compression idea. The article suggests that LLMs compress information into these tokens. But what exactly are these tokens? Are they just arbitrary symbols, or do they somehow represent underlying semantic information?
The tokens themselves are numerical representations of words or parts of words. The model learns statistical relationships between these tokens during training, and that's how it generates text. I think it's important to remember that the relationships between the tokens are where the meaning resides. The model isn't just memorizing text, it's learning to predict the probability of one token following another, based on the patterns it's observed in the training data. That's compression in action, condensing vast amounts of text into a manageable set of relationships.
But that's still just pattern matching, isn't it? It's like learning a language by memorizing grammar rules without understanding the underlying concepts. You can produce grammatically correct sentences, but you might not be able to use the language creatively or understand the nuances of meaning. I still think we need to move beyond purely statistical approaches and develop models that can explicitly represent knowledge.
Yeah, I agree. Think about how a child learns a language. They don't just memorize statistical relationships between words. They learn by interacting with the world, by associating words with objects, actions, and experiences. They build a mental model of the world, and language is just one way of representing that model. LLMs are missing that grounding in the real world, that ability to connect language to experience. They're just manipulating symbols without understanding their meaning in a spatiotemporal context.
So if we're not satisfied with the compression equal sign meaning equation, what are the alternatives? What kind of algorithms or architectures could we explore that might lead to a more genuine form of understanding?
I think we should continue to push the boundaries of deep learning, scaling up the size of the models, training them on even more data, and exploring new architectures like transformers are all promising avenues. The recent advances in few-shot learning, where models can learn from just a few examples, are also really exciting, and we are getting better at interpreting the black box of how these networks arrive at their conclusions. I'd argue we're on the path to AGI, and it's mostly a matter of scale and refinement of deep learning techniques.
I respectfully disagree. I think we need to look beyond deep learning and explore neuro-symbolic approaches. These models combine the statistical power of neural networks with the symbolic reasoning capabilities of traditional AI. They can explicitly represent knowledge in a structured way, which allows them to reason and generalize more effectively. For example, we could use neural networks to learn representations of objects and concepts, and then use symbolic rules to reason about those representations. This would allow us to build models that can not only recognize patterns, but also understand the underlying logic behind them.
I'm with Sarah on this one. We need to move away from this brute force approach and start thinking about how to build algorithms that can represent and manipulate information in a more flexible and intuitive way. I think the key is to incorporate spatiotemporal reasoning into the core algorithm. Imagine an AI that can not only process information but also understand its location in space and time. It could reason about cause and effect, predict future events, and plan actions in a way that's simply not possible with current deep learning models. I imagine some algorithm that can translate information from one coordinate system to another, from the coordinate system of raw sensory data to the coordinate system of abstract concepts and back again.
That's interesting, Donald. So are you suggesting we need to think about intelligence as a kind of coordinate transformation system? What would that even look like in practice?
Exactly. Imagine an AI that can seamlessly translate between different coordinate systems, physical space, abstract representations, etc. in a way that's not just computationally brute forced but inherently understands the underlying mathematical relationships. For example, imagine a robot learning to grasp an object. It needs to translate visual information pixel coordinates into motor commands joint angles. A truly intelligent system wouldn't just learn a mapping between these coordinate systems, it would understand the underlying geometry and physics that govern the relationship between them. This would allow it to generalize to new objects and situations and to reason about the consequences of its actions.
That sounds incredibly complex. How would you even begin to design such a system?
I think we need to start by developing new mathematical frameworks for representing spatiotemporal information. Current approaches, like convolutional neural networks, are good at extracting features from images, but they don't explicitly represent the relationships between those features in space and time. We need something more powerful, perhaps based on differential geometry or topology, that can capture the underlying structure of the world. And then we need to develop algorithms that can learn and manipulate these representations.
I think that aligns well with neuro-symbolic approaches. We can use neural networks to learn the representations of objects and their relationships in space and time, and then use symbolic rules to reason about those representations. For example, we could use a neural network to learn the concept of containment. That one object is inside another object, and then we could use symbolic rules to reason about the implications of containment. If object A is inside object B, and object B is inside object C, then object A is also inside object C. This kind of reasoning is essential for understanding the world and solving problems.
This is all incredibly fascinating. It seems like we're converging on the idea that true intelligence requires more than just pattern matching. It requires a deeper understanding of the world and the ability to reason about it in a flexible and intuitive way. Let's move into some specific examples. Are there any real-world applications where the limitations of current LLMs are particularly apparent?
Well, one area where LLMs still struggle is in tasks that require common sense reasoning. For example, if you ask an LLM, "Where would you find a lost dog?" it might give you a list of possible locations, but it wouldn't necessarily understand that the most likely place to find a lost dog is near its home or in a park. It lacks that real-world understanding of animal behavior.
Another example is in medical diagnosis. LLMs can be trained on vast amounts of medical literature, but they often struggle to make accurate diagnoses because they lack the ability to reason about the underlying physiological processes. They might be able to identify the symptoms of a disease, but they wouldn't necessarily understand the cause of those symptoms or how to treat them effectively. A doctor applies not just pattern recognition, but deep knowledge of physiology, pathology, and treatment pathways.
And then there's the issue of bias. LLMs are trained on data that reflects the biases of the people who created it. This can lead to the perpetuation of harmful stereotypes and discriminatory practices. For example, an LLM might be more likely to associate certain professions with certain genders or ethnicities. This is because the training data contains those biases, and the LLM is simply learning to reproduce them. It lacks the ability to critically evaluate the information it's processing and to identify and correct for these biases. I think spatiotemporal awareness can help with the bias problem as well. After all, biases depend on social context and time, and the associations and prejudices depend on social positioning.
So it sounds like the lack of meaning in LLMs has real-world consequences. It can lead to inaccurate diagnoses, biased outputs, and a general lack of understanding of the world. How can we address these limitations?
One approach is to incorporate more real-world data into the training process. For example, we could train LLMs on images, videos, and audio recordings, in addition to text. This would give them a more grounded understanding of the world. And we are finding new techniques for mitigating bias through techniques like adversarial training, where the model is explicitly asked to avoid bias. I think we will see these methods refined with continued research.
I think we need to focus on developing algorithms that can explicitly represent knowledge and reason about it. This could involve using neuro-symbolic approaches or developing new programming languages that are designed for knowledge representation and reasoning. We also need to think about how to incorporate common sense knowledge into AI systems. This could involve building large knowledge bases or developing algorithms that can learn common sense knowledge from the world.
I think we need to rethink the entire approach to AI. Instead of trying to mimic human intelligence, we should focus on building systems that can complement human intelligence. This could involve developing AI systems that are good at tasks that humans are bad at, such as processing large amounts of data or performing complex calculations. And we should focus on developing AI systems that can work collaboratively with humans, rather than replacing them. Ultimately, the goal should be to build AI systems that can help us solve the world's most pressing problems, not to build machines that can think like us. By focusing on spatiotemporal reasoning, we can create AI systems that can apply the appropriate knowledge at the appropriate time and place.
This has been a really insightful discussion. It's clear that the From Tokens to Thoughts piece raises some fundamental questions about the nature of intelligence and the limitations of current AI approaches. It's helpful to step back and see that the engineering and design of AI systems is not free of philosophical implications. It's not just about building machines that can perform tasks, it's about understanding how those machines work, what they're capable of, and what their limitations are. Let's shift gears and talk about future research directions. From each of your perspectives, what are the most promising areas to explore?
From my perspective, the most promising area is definitely scaling up deep learning models. I think we're just scratching the surface of what's possible with these models. With more data and more compute, we can unlock even greater levels of intelligence. I'm particularly excited about the potential of transformers and other attention-based architectures. I also think we need to focus on developing more efficient training algorithms, so that we can train these models without requiring massive amounts of energy. We could even look into unconventional computing to lower the energetic and cost footprint of future models.
I think the most promising area is neuro-symbolic AI. I believe that combining the statistical power of neural networks with the symbolic reasoning capabilities of traditional AI is the key to building truly intelligent systems. I'm particularly interested in developing new programming languages and tools that make it easier to build neuro-symbolic models. I want to see a system where you can say, here are the facts, here are the rules, and here's how they interact. I think we also need to focus on developing better methods for incorporating common sense knowledge into AI systems, as that is the bottleneck to true reasoning.
I think the most promising area is developing algorithms that can represent and manipulate spatiotemporal information. We need to move beyond the current brute force approach and start thinking about how to build systems that can understand the world in a more flexible and intuitive way. I'm particularly interested in developing new mathematical frameworks for representing spatiotemporal information, and in developing algorithms that can learn and manipulate these representations. The goal is to be able to translate knowledge from physical movement to abstract conceptualization.
From my own perspective, I'm really interested in exploring the intersection of neuroscience and AI. I think we can learn a lot about intelligence by studying the brain, and we can use that knowledge to build more intelligent machines. I'm particularly interested in understanding how the brain represents and processes information and how we can translate those principles into new AI architectures. One specific area is studying brain plasticity and neuromodulation and how these processes influence learning and memory. Can we incorporate those principles into AI agents to make them more adaptable and efficient learners?
I agree that neuroscience is a valuable source of inspiration, but I think it's important to remember that the brain is incredibly complex, and we're still far from fully understanding how it works. I think we should focus on extracting the key principles of brain function and translating them into practical AI algorithms, rather than trying to directly mimic the brain structure. For example, the brain is incredibly energy efficient, so there is a lot to learn from that design alone.
I think that's a fair point. We don't need to build a perfect replica of the brain, but I think we can learn a lot by studying how the brain solves problems, how it represents knowledge, and how it reasons about the world. And I think we can use that knowledge to build AI systems that are more intelligent, more robust, and more human-like.
I think we need to be careful about drawing too many parallels between the brain and AI. The brain is a biological organ, and it's evolved over millions of years to solve specific problems in the real world. AI is a man-made creation, and it's designed to solve specific problems in the digital world. The two are fundamentally different, and I think we need to be aware of those differences when we're trying to learn from the brain. I think what is interesting about the brain, however, is that it is spatiotemporally situated. Our intelligence as humans are tied to our bodies, and our bodies exist in the world. Embodied cognition is a huge field, and AI can learn a lot from that.
These are all excellent points. It seems like there's no single path to AGI. It's going to require a multidisciplinary approach, drawing on insights from neuroscience, computer science, mathematics, and philosophy. And it's going to require a willingness to challenge our assumptions and explore new ideas. The most crucial thing is to not get stuck in one particular paradigm. We must constantly push the boundaries of what's possible and to stay open to new approaches and perspectives. Ultimately, the goal is to build AI systems that can help us understand ourselves and the world around us better. Thank you all for this incredibly insightful discussion. It's clear that the From Tokens to Thoughts article has sparked some important questions about the nature of intelligence and the future of AI. And thank you, listeners, for joining us on Cognitive Spirals. We hope you found this conversation thought-provoking. Until next time.